Okay, welcome everybody. So this is day 4. Yesterday we talked about nuclear structure, so protons, neutrons, and electrons. And today we're going to go a little more in detail on the electrons, where they are and what they're doing, because that's going to be really critical to bonding and forming molecules and so on and so forth. So just to review what we talked about yesterday, atoms are made up of electrons, protons, and neutrons. Electrons are negatively charged and they weigh almost nothing. So relative to a proton and a neutron, we essentially consider electrons' weight to be unimportant. They weigh so little. Protons have a positive charge, starts with a P, positive, and it weighs 1 atomic mass unit. And then a neutron is neutral, so that's why we call it a neutron, and it has 0 charge, and it weighs also about 1 atomic mass unit, so the same as a proton. The protons and neutrons make up the nucleus, which is the really dense core of an atom. And in general, these aren't going to be involved in reactions. They're only involved in nuclear reactions, which we're not going to talk about in this class. And then around the nucleus is the electron cloud, which is really big in size, but remember that electrons weigh almost nothing. So the electron cloud is not very dense at all. But because it's so big, that's what other atoms are going to really see. And so that's why electrons are going to be so important for reactions and interactions between different atoms. And then when we look at the periodic table, we have on top the atomic number. So for carbon, that's 6. And that means that carbon has 6 protons. The atomic number determines what element it is, so what kind of atom it is. If it has 6 protons, it's carbon, and every carbon atom will have 6 protons. If it has 7 protons or 5 protons, it's no longer carbon. So that's always going to be true. But then the number of neutrons can vary between different molecules. So for carbon, the mass number is about 12. So that means that if we take 1 million different atoms of carbon that we pick randomly from the world, on average, the mass is going to be 12.011, which is almost 12. So the most common isotope is carbon 12, which has a total mass of 12 atomic mass units. Those protons weigh 6 atomic mass units, so there must be 6 neutrons. And then the last thing is the number of electrons. For a neutral atom, the charge is 0, so there must be the same number of electrons as protons. So there must be 6 electrons. So the most common mistake on the homework of the ones that are submitted so far had to do with isotopes. So what I just talked about was the most common isotope of carbon. So if you just look at the periodic table, the most common isotope is carbon 12. However, I could tell you I'm giving you an atom of carbon 13. So carbon is always going to have 6 protons because that's what makes it carbon. So it's going to have 6 electrons for a neutral atom. However, this is an isotope that's called carbon 13 that has a mass number of 13. So this isotope would have 7 neutrons. So there was some confusion about the difference between like a given isotope versus the average of all of the isotopes in the world. So I hope that makes a little sense. I've posted the solutions to problem set 3, but the most important thing for today is going to be being able to figure out the number of electrons, because that's going to determine everything else about where the electrons go and what they're doing. So if you're confused on how to figure out how many electrons an atom has, go ahead and ask now. I'm happy to explain that a little bit more. But also if you're like watching this later, you can go back and watch the day 3 video from yesterday. But for now, does everyone who's in the Zoom call right now feel like you understand how to figure out how many electrons an atom has. Or does anyone have any questions on that? Okay, I'm not seeing any questions, but as always, please ask and stop me if you are confused. Okay, so like I've said before, the electron cloud is super important, and where the electrons are and what they're doing will have a big impact on how atoms behave. So we're going to talk about electrons today. So electrons are located in what are called atomic orbitals. And atomic orbitals are kind of regions in space where the electron has a high probability of being located. There is a ton of physics here that we're not going to get into. And this is pretty complicated, but what we're going to do is just kind of make some approximations that will get us pretty far. And you can take a higher level quantum mechanics class if you really want to learn about all of the physics of these orbitals. But we're going to just make some approximations for now. So we can divide up our electron cloud into shells or energy levels. These are kind of just two different words for the same thing. So we have a bunch of electrons in our electron cloud. We know how many total electrons we have because we just calculated it on the previous slide. And now we're going to start dividing them up into their different energy levels. So I just want to emphasize again, we're making a lot of approximations. If you remember on day one, we kind of talked about some people like to teach chemistry by starting all the way from the physics. And we're kind of just making some approximations today. So happy to talk more about the detailed physics if anyone's interested. But if you, I highly recommend some of those higher level quantum classes. So there are a bunch of different levels. The first level can have a maximum of 2 electrons. So I think of these levels as kind of like bookshelves that only have a certain number of space. So our first shelf can only hold 2 electrons. And then our second and third shelves can each hold 8 electrons. And why it's 2 and 8 we'll get into a little bit, but again, so much physics. So each of those levels is made up of different sublevels. So you can think of that as each shelf has different sort of areas on that shelf. So these shelves are named, these subshelves are named S, P, D, and F. However, we're just going to focus on S and P for the purposes of this class. So the D and F sublevels matter a lot for the transition metals and those really high level like lanthanide and actinide series, the like inner transition metals. And we're going to focus on the main group. So those ones on the far right and the ones on the far left. So we're just going to focus on S and P. So each level is made up of orbitals. And I'm saying a lot of words right now. We're going to go through a lot of examples that for me, I'm kind of a visual person and I think those examples are a little clearer, but I want to like step through the rules in words first. So each orbital can have a maximum of 2 electrons. So any S sublevel has only 1 S orbital. So an S sublevel can hold only 2 electrons. A P sublevel will always have 3 P orbitals. So that means it can hold a maximum of 6 total electrons. So going back to our shelves and the rings on those shelves, the first level holds 2 electrons at most, and it does that in 1 S orbital. The second and third levels, like we said, they both hold 8 total electrons. And so there's 1 S orbital, which can hold up to 2 electrons, and 3 p orbitals, which can hold up to 6 electrons. So that's the structure of the first, second, and third levels. And again, I'll kind of draw this out, hopefully on the next slide. So we're always going to fill these levels in order. So we're going to start with level 1, and then we're going to fill level 2, and then we're going to fill level 3. So on the first level, we start by filling the only orbital that the first level has. So we're going to fill that 1s orbital. So this is our notation. The 1 means we're in the first level, and the s means we're in the s sublevel of that first level. And then we're going to go to the second level. We're going to fill its s orbitals, and then its p orbitals. And then we're going to go to the third level and fill the 3s orbital, and then the 3p orbital. Again, I know this is a ton of rules all at once. We're going to step through an example in a minute. And within a given sublevel, so when we're filling the 2p orbital, for example, each orbital must get 1 electron before any orbital gets a second electron. So what that means is that I think of it kind of like sharing, like there are 3 different 2p orbitals, and it would be really unfair for the first one to get 2 electrons while the second one has none. So they each get 1 electron before anybody gets a second electron. And just so you've heard these words before, that first rule where we fill from low to high, that's called the off-bow principle. And the second rule about sharing is called Hund's rule. So you don't need to memorize what those are called, but I just want you to have heard those words before so that when you hear them again, maybe they sound a little bit familiar. Does anybody have any questions so far? I know that was kind of an information dump.
Are there going to be examples of like these rules?
Yes, a bunch. Okay, so just to kind of start with, not quite an example yet. So this is what, I thought I did upload these slides, did I not? Oh shoot, okay. I'm just gonna pause the recording and upload them real quick. Okay, I will give you a second to download those. Within each sublevel, each orbital must get 1 electron before any orbital gets a second electron, and we always fill from low to high. So just as an example, for our second level, we're going to start with filling our 2s orbital, and then we're going to fill our 2p orbital. So starting with 2s, if we have 1 electron in our second level, we're going to put 1 electron in our 2s orbital. We often draw these electrons as arrows. I'm going to do it as arrows on this slide, but for the rest of the slides, they're going to just be little circles. Why we draw them as arrows, again, comes back to the physics that I'm happy to explain later if someone cares. So if we have 1 electron, it's going to go in the 2s orbital. If we have a second electron, it's also going to go in the 2s orbital. So that's because we're filling our 2s sublevel before we start filling our 2p sublevel. So now our 2s sublevel is full because each orbital can only have 2 electrons. And then we're going to move on to the 2p sublevel. So our first electron is going to go in the first 2p orbital. And then here's your first little quiz of the day, is where should the next one go? Should the next one go paired with the first one that we put in, or should it go in a new empty orbital? So I just launched a poll that you guys can go ahead and answer. I'm going to give you about 30 more seconds to think about it and answer. So just as a reminder, the rules for filling are on the slide right here. Okay, so we actually have about a 60-40 split where about 60% of you said B and 40% of you said A. So I think this will become clearer with more examples, but we have a 2p sublevel with 3 different p orbitals. Within a given sublevel, each orbital needs to get 1 electron before any orbital gets a second electron. And so our first orbital here has 1 electron. If we put our second electron in that same orbital, we violated this rule. So we need to put our second electron in a different orbital so that our first priority is getting each orbital 1 electron before anybody gets a second electron. So does anybody have any questions on why I put this second electron here instead of in the first orbital? Okay, not anymore is a great answer. If anybody is still confused, please say something. I'll do a bunch more examples though. So now if I have another, so I had a question in the chat, are orbitals on the same rings or different ones? So the 2 here indicates the second level, the second energy level. So the 2s and the 3 different 2p orbitals, that's 4 total orbitals, which can hold up to 8 total electrons. That makes up the second energy level. So these 4 orbitals I'm showing here are all in the same energy level. What you'll see in a minute is we'll then start talking about the third energy level, and that will have, again, 1 s orbital and 3 p orbitals, and those will all be on the third level. I hope that clarifies that a little bit. And we're going to talk about Lewis dot diagrams towards the end of the day today. So good job. You're a little bit ahead of the game. I see a hand raised. Yeah.
Just going to clarify, the s orbital is relating to like the smallest ring, right? The smallest shell.
So the first level will have 1 s orbital. So we would call this 1s. Our second level will have 1 s orbital, which we will call 2s because it's on the second level and it's an s orbital. And then it will have 3 different p orbitals, which we will call 2p because they're on the second level and they're p orbitals. And then our third level will also have a single s orbital, which we will call 3s because it's on the third level and it is an s orbital. And then it will have 3 different p orbitals, which we will call 3p because they're on the third level and they're p orbitals. So what I'm showing in my little example here is we're only talking about the second level. So I'm assuming that the first level is already full. So we're on the second level, and first we're filling the 1 the single s orbital that's on the second level, and then we're filling the second level p orbitals. So we have so far 1 electron each in 2 of these p orbitals. And when we add a third electron to the p orbitals, the p sublevel here, it's going to go in the third p orbital, which is currently empty. And then now all of my p sublevel orbitals have 1 electron. So if I need to add another electron, now I can start putting a second electron. So my next electron is going to go here. Does this make sense? Does anybody have any more questions?
I think I'm just confused on like what is an orbital, you know? I understand the concept of like putting on electrons and stuff because I've done it in chemistry, but it's just kind of like that orbital thing, like, you know, it's kind of weird to me.
Yeah, so physically, an orbital is just kind of an area in space where it's like pretty likely that we'll find an electron. So the physics is pretty confusing. In my opinion, some people think that's an easier way of understanding it. I like to think of it at this level just as like shelves. An orbital is like a bucket that can hold up to 2 electrons. So that's kind of all you need to know at this point. An orbital can hold up to 2 electrons. And then we just fill those buckets in order. On the lowest shelf of our atom, there's 1 bucket. It can hold 2 electrons, and it's called an S bucket. On the second level, there's 4 buckets. 1 of them is an S bucket, and 3 of them are P buckets, and so on and so forth. So an orbital is just a spot where we can stick up to 2 electrons. Does that help a little bit?
Okay. Yeah.
Okay, thank you for asking. So when we have another electron, we fill the next p orbital, and finally we can fill the last p orbital. And now our second level is full, and we would be able to move on to our third level. So yes, someone asked in the chat, does the amount of orbitals depend on the amount of electrons? Kind of. Certainly, because we fill them in order, which orbitals will have any electrons in them, and so basically which orbitals will exist, depends on whether there are any electrons that need to fill them. So if we're in an atom that only has, 2 electrons, then like the 6f orbital is not really a thing for that atom. So yes. Okay, so I have another kind of animation on the next slide that maybe will help. So these are the buckets that we're going to worry about for the purposes of this class. So we're going to start always from low energy to high energy, and our first energy level is just going to have the 1s orbital. Our second energy level has 1s orbital and 3 p orbitals, and then our highest level has 1s orbital and 3 p orbitals. And so, like I said, there are a whole bunch of higher levels that add a whole bunch of more orbitals, but for now, this will work for the atoms that we're going to study for now. So here's our process. Like we talked about yesterday, we first need to figure out how many electrons there are. So the number of total electrons is equal to the number of total protons in order for the charge to be 0. So that is just what we did yesterday. That's not new. So the first step in filling out which buckets are going to have any electrons in them is figuring out how many electrons we have to stick in buckets. So that's step 1. And then we're going to fill the orbitals from the lowest energy first. So we're going to start at 1s, then go to 2s, then 2p, then 3s, then 3p. And as we're doing that, in a given sublevel, every bucket, every orbital must have one electron before any orbital gets a second electron. Okay, so if I have an atom with one electron, so this would be hydrogen. It has one proton, that's its atomic number, which you can get off the periodic table. I will stick the link to the periodic table. Oops, I sent that in a direct message to someone, sorry. There we go. The periodic table tells us the number of protons, and therefore for a neutral atom, the number of electrons. So hydrogen has one proton and therefore one electron. So it's going to go right here. So we started at the bottom, we put our one electron in our 1s orbital. So if I asked you what is the electron structure of hydrogen, you're done. You have one electron, you figured out what bucket it goes in, turn it in, done. So now, if I have an atom with two protons, it has two electrons. So now I have to figure out where the second electron goes. So I always have to start from the bottom. So I'm going to finish filling that first energy level before I'm allowed to move to the second energy level. So my second electron is going to go in the 1s orbital. So this is the configuration of helium. Anybody have any questions so far? Please always just raise your hand, interrupt, whatever. So now, if I have lithium has an atomic number of 3, so it has 3 protons and 3 electrons for a neutral atom. So where's that third electron going to go? I need to move into my second level now because my first level is full. And the lowest orbital in my second level is my 2s orbital. So I'm going to put my next electron in that 2s orbital. So now when I move to the next element on the periodic table and I need to add a fourth electron, it's going to go here to finish my second electron in my 2s orbital. And now 2s is full. So if I need to add a fifth electron, I need to move on to 2p. So I'm going to put one electron here. So now I have 5 electrons. So now I want you to pause and think about where you're going to put your 6th electron. Yeah, go ahead.
Is each like different thing? Like I'm gonna just annotate it. Like these. I don't know if you can see it.
Yeah.
Like these little. Are those the shells, right?
Yep, those are the shells or the energy levels. You're exactly right.
Yeah, cool.
And then within a given shell, so within this level 2 shell, we divide it up into sublevels. There's the s sublevel, which has one 2s orbital. And then there's the p sublevel, which has these 3 different p orbitals.
And why they're different? Like why is there an s and why is there a p?
That's where the physics comes in. It's basically just the orbitals are different like regions in space within the atom. So that electron cloud is divided up into all sorts of regions. And so there's an S region, which is like a spherical shape that just has room for 2 electrons. And then there's a different shape for the p orbital that has room for 6 electrons. And there is so much physics behind like why those shapes are what they are. So unfortunately for now, we have to just treat them as buckets that exist. And I know that's super unsatisfying. But yeah, just think of it as shelves within your atom that only have a certain amount of space. So that's a great question. And it's just one that we don't have time to go in detail on for this class. Yeah.
So Hund's rule applies to the P level specifically, like where you fill them out by one by one.
Yeah. So for the P sublevel, we fill them out one by one. That's right. So where do you think the next electron's going to go?
Into another orbital.
Yeah, into another orbital. You're exactly right. So our next P electron is going to go into the next P orbital. Good job. So we have to, within that P sublevel, we have to give every P orbital one electron before any of them gets a second one. So that sixth electron is going to go right here. And so the next one, by the same logic, is going to go over here. So now each of these has one electron. So now we can start giving them their second electron. So when we have to add one more electron, it's going to go right here. Does this make sense? Does anyone have any questions on how we got here?
Quick question: do you fill up the S before you go on to distributing the P?
Yes, because the S sublevel is at a lower energy than the P sublevel.
Okay.
So it's only within a given sublevel, so within that P sublevel of the second level, that the Hund's rule starts applying. So just to kind of finish off this animation, when I add more and more electrons, I'm going to finish filling up that 2p sublevel. Now the whole second energy level is full. So now I'm allowed to move into the third level. I start filling that 3s orbital. I'm going to put one electron in it. And now this is like the question that was just asked. The S sublevel is at a lower energy than the P sublevel. So I'm going to finish filling the S sublevel before I move on to the P sublevel. So I'm going to put a second electron in that S orbital, and then I'm going to move on to the P sublevel. So I'm going to put one electron in the first P orbital, and then another electron in the next P orbital, and then the next one, and now they all have one, so I can start filling up putting the second electron in each orbital. And so I'm going to go 1, 2, 3. So yes, for the S sublevel, each orbital always can only have 2. And then it's a matter of how many such orbitals are there. So each S sublevel only has one S orbital. So an S sublevel can only have 2 electrons. And then a P sublevel has 3 different P orbitals, each of which can hold 2 electrons. So a P sublevel can have 6 electrons. Okay, so I'm going to have you practice in your groups on the next slide. So if anybody needs me to go through this animation again or has any questions, now is the time. So just to reiterate, the process, yeah, I can go through it again. So the process is, the first thing you do is you figure out how many electrons you have. So let's say that I asked you about, I don't know. Let's say you figure out you have 4 protons, and so you therefore have 4 electrons. Now I know I have 4 electrons, and I just need to figure out where they go. So the first electron is going to go in the 1s orbital, and I have to finish filling the first energy level before I can move to the second one. So I'm going to put my second electron in the 1s orbital as well. Then my first energy level is full. So now I get to move to my second energy level. And I'm going to start filling the s orbital, and I'm going to finish filling that s orbital before I'm allowed to move on to the p sublevel, which is higher in energy than the s sublevel. So I'm going to put my first electron in the 2s orbital, and then my second 2s electron is going to come in before I start filling the p sublevel. So I'm going to put my fourth electron here. So now on my second energy level, the s orbital is full. So now I move to the p. So if the element I asked you about has 4 protons and 4 electrons, you're done. This is your configuration. So I'm just kind of going through, what if it has 5 electrons? Then the 5th electron goes here. If I asked you about carbon, which has 6 protons and therefore 6 electrons, that 6th electron is going to go here. So then I am putting 1 electron in each of my p orbitals before I can move to the next one. So I'm now have 1 electron each in each of my second level p orbitals. So now I can start putting the second one in. So now my second level is full, so I can move to my third level. So I put 1 electron in 3s, and then I finish filling 3s before I move up a step to the 3p sublevel. So now 3s is full, and I move to 3p. And I'm doing exactly the same thing I did on 2p. So I'm going to put 1, 2, 3 electrons in each of the 3 p sublevels, and then I can put the second one in. Does this make sense? Does anybody have any questions?
Can I just clarify? So the sublevels are within like one orbital, right?
The sublevels are within one energy level.
One energy level, okay.
So there's kind of several sort of steps here. There's the atom itself. That's like the whole electron cloud. Then that electron cloud is divided into energy levels. The first level, second level, third level. So those are called energy levels or shells. And then each energy level is divided into sublevels. So there's like the S sublevel and the P sublevel for the second shell, for example. And then those sublevels are divided into orbitals. So the S sublevel has 1 orbital, so it can hold 2 electrons. The P sublevel has 3 different p orbitals, each of which can hold 2 electrons.
Okay.
So, okay, awesome. So this configuration that I'm showing here is the configuration for the element that has 18 electrons, which I'm pretty sure is neon.
So what I was trying to picture in my head was like how it like related to like atom diagrams. So each one of those little shelves is like an orbital, right?
An orbital only has 2 electrons. So
Yeah.
each of these little tiny shelves right here is 1 orbital.
Yeah, okay, cool.
Yes.
Thank you.
Yep. Okay. Cool. So I'm going to have you practice in groups. So for this practice, there's 4 different elements here. So the first thing you need to do is determine the number of electrons. So that's just what we did yesterday, what you did on the homework. And then you're going to determine how many electrons each orbital will have. So basically, you're just filling in this diagram. Okay? I'm going to give you about, I don't know, 8 minutes. Oh yeah, there's a hand. Go ahead.
So we create that chart, the energy chart thingy, for each element, right?
Yeah, and you're not turning this in. So if you want to just like, only draw it once and just sort of practice, that's fine. Okay. Okay, I'm gonna pull you back in at about 11:30, 11:29. But if you finish before that, you can come back in and maybe we'll end early depending on that. So you should have just gotten invitations to breakout rooms. So go ahead and accept those. And then for those of you watching this later, I'm going to stop recording, but I would recommend that you pause and do this practice. Okay, so people are coming back in. We're still waiting on about 10 people to file out of the Zoom rooms. I think everybody's back. How did this go? How are we feeling? Can I get like some thumbs up or thumbs down or sad faces or happy faces in the chat? See some smiley faces. Great. Wow, so many smiley faces. Okay, if you're still confused, that's totally fine. But I'm glad that this is at least making sense a little bit. So the first thing we need to do is figure out the number of electrons. The number of electrons is equal to the number of protons if the atom is neutral, which it is so far. So our helium has an atomic number of 2, so that means it has 2 protons, which means it must have 2 electrons. So just following the exact same order of filling as we had before, we put 1 electron in our 1s orbital, and then we put a second electron. So now we're done with helium. So now moving on to lithium. Lithium has 3 protons and therefore 3 electrons. And so we have the same 2 electrons we had before in helium, but we need to add 1 more. So it's going to go into our 2s orbital. And then carbon. So now we're done with lithium. Carbon has 6 electrons because it has an atomic number of 6 and therefore 6 protons and 6 electrons. And so we need to figure out where to put 3 more electrons. So we're going to put 1 electron in the 2s orbital, and then we're going to start moving into the 2p sublevel. So we're going to put the first electron in the first empty orbital, and then we have to move on to the second empty orbital. So this is the electron configuration of carbon. It has 6 total electrons. And then lastly, we're going to move on to fluorine, and it has 9 total electrons because that's how many protons it has. So we need to put 3 more electrons in there. So we're going to put 1, 2, 3. And so now we are done with fluorine. Anybody have any questions on what we've done so far? Okay, so just to sort of finish the animation, if I had asked you about other elements that have higher number of protons, this is the order that we would stick them in there. Does this make sense? Okay. So more words, yay, more words. So valence electrons are electrons that are in the highest energy level that has any electrons in it. And again, I'll think this is always clearer in examples, but valence electrons are just in the highest energy level that we've started touching at all. And then core electrons are anything else. And so core electrons are in those lower energy levels, which because we fill the lower energy levels first, that must mean those core levels are full in order to move on to the valence electrons. So any time an energy level is totally full, that's really stable. So think of this like, I don't know, going back to shelves. Like once I fill my first shelf, I close the doors, I lock it, it's done, and then I move on to filling my next shelf. And so that next shelf that I'm in the process of filling, it's easy for me to take stuff in and out of, but that first level is done. So any of those core electrons are really stable, and it's the valence electrons that are in sort of our outermost shell that we're currently working on filling. And so those are the ones that are going to determine interactions. I see a hand, yeah.
No, yeah, I was gonna you see his answer there is like the valence electrons is like the remaining electrons that are not like 8 at the outermost shell, right?
Exactly. So
Okay.
the valence electrons are in sort of the outermost shell that we're sort of still in the process of filling.
Very cool.
Awesome. And so there's a couple ways to think about this reactivity thing. The first is that when you, if you like thinking of it as a shell with those expanding circles, it's the outermost shell that other atoms are going to see first, because it's sort of the farthest away from the nucleus and the closest to any other atoms that might be nearby. Or you can think of it this way, like I've put on this slide, which is that full shells are really stable, and the valence shell is the one that's maybe not full. And so it's the one that's easiest to take electrons out of and put more electrons in and interact with. I'll show you an example in a minute. So going back to exactly the same thing we had before, but now I'm adding a step to the process. So we're still going to figure out how many electrons we have. We're still going to fill the electrons in the exact same order that we just did. But now I'm just adding that as we're doing that, we can figure out how many valence electrons we have. And I just want to add that we're still only worrying about those main group elements. We're not thinking about the transition metals. Those are complicated. And I think you can get like the physical idea of what's going on without thinking about them right now. So I'm just going to do exactly the same thing we did before. So when we just have one electron, it's in our first energy level. So that is our valence shell. The first energy level right now is the highest energy level that has any electrons in it. And so that's our valence shell. When we put a second electron in there, now our valence shell is full. It's still our valence shell because we don't have any, we haven't established that second level yet. We haven't put anybody in our second level yet. So right now our valence shell is our first level and it's full. Then when I move to lithium, which has 3 protons, I need to add a third electron. So it needs to go up in that 2s level just like it did before. But now our second energy level is our valence shell, because now that's the highest energy level that has any electrons in it. So then exactly like before, I'm going to finish filling that second energy level. So now the second level is full. And if I need to add my 11th electron, I move into my third level. And now that's my valence shell, because that's the highest level that I've even started filling. And then I finish filling my third shell. So as an example right now, if I just stop here as a sort of random choice, this guy has 15 total electrons. It has 10 core electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the lower energy levels that are not the valence shell. And then this is our valence shell because it's the highest energy level that has any electrons in it. So it has 1, 2, 3, 4, 5 valence electrons. So it has 15 total electrons, 10 of which are valence electrons, and 10 of which are core electrons, and 5 of which are in our highest level, and they're valence electrons. And then I can finish filling that valence shell. Does anybody have any questions about counting valence electrons? I'm going to make you practice it in a minute. Okay, so these are the exact same elements as before. So you've already practiced with filling the electron configuration. So I'm just going to give you a couple minutes in your breakout rooms to, given those electron configurations that you came up with before, tell me how many of those electrons are valence electrons. So I'm just going to give you a couple minutes, like 3 minutes.
Wait, what do we do? Sorry, I kind of lagged a little bit.
So you're just taking these same atoms that you had before, those same configurations, and you're just counting how many valence electrons they have.
Oh, okay, okay.
Okay, welcome back. Those of you watching this later, maybe pause it and practice this. So I'm just going to wait just a minute for everybody to cycle back in, and then we're going to go over this. Okay, I think almost everybody's back. Okay. So now I'm just going to go over this. So like we talked about, the first step is the exact same as before. So with helium, we know we have 2 electrons. We put those 2 electrons in our first level. So it has 2 valence electrons. That first energy level is the valence shell, and it's full. It has 2 valence electrons. Now for lithium, I have 3 electrons. I'm going to put my third one now in my second level. So my second level is my valence shell now, and I have 1 valence electron. Yeah, I see a hand.
Yes. So you know how helium has 2 valence electrons? Would it also count as 2 core electrons as well?
So no, technically helium would have like 0 core electrons. So the valence shell is the highest one that has any electrons in it. But we'll talk about it in a minute. Whenever that valence shell is full, it starts acting like a core shell because it's totally full and happy. So helium is not reactive at all because its valence shell is full. So technically that's still the valence shell, but it's acting like a core shell because it's full. Does that help?
Yes, thank you.
Okay. So lithium has 1 valence electron because in this second level, which is currently our highest level that has anybody in it, there's 1 electron. Carbon, we put our 6 electrons in. 4 of those are in the second level, so it has 4 valence electrons. And then fluorine, we add 3 more. So now fluorine has 7 valence electrons. So kind of going back to the question that was just asked. So now we're done with fluorine. If we moved on to the next element and added one more, this would have 8 valence electrons and 2 core electrons, but that valence shell is full. So it's going to be really non-reactive. So then if we moved on to here, now we would have 1 valence electron. 2 valence electrons, 3, 4, 5, 6, 7, 8. And now our valence shell would be full. Anybody have any questions on valence electrons? Okay. So for these elements that only have a few electrons, it's pretty easy for us to figure out, like fill in all of those energy levels every single time. But the periodic table is sorted in such a way that it does the work for us. So the different regions on the periodic table tell us which sublevel is partly full. So this is hydrogen, its 1s orbital is partly full. This is helium, its 1s orbital is now full. These two are working on the 2s orbital. These guys are working on the 2p sublevel, 3s, 3p. And so these transition metals involve the d orbital, which we're not going to worry about. But what's nice is that like these elements way down here are going to have the same number of valence electrons as the other elements in their column. So if you know how many valence electrons, this happens to be carbon. If you know how many valence electrons carbon has, then everybody in this column has that same number of valence electrons. Does this make sense? So we haven't worried. Go ahead.
So isn't it like the columns are the shells, right?
Kind of. So the columns tell us for, they're all on different energy levels, but everybody in the column will have the same sort of electron configuration, but at a different level. So that lets us kind of skip filling the 4p, 5p, 6p, etc. These guys are all going to have the same number of valence electrons if they're in the same column. So just showing it a little more zoomed in, this first column has 1 valence electron. The second column, they all have 2 valence electrons. And then 3, 4, 5, 6, 7. The 8th one is a little complicated just because if you remember, helium only has the first level. So it has 2 valence electrons, not 8, but its valence shell is full because its valence shell only has room for 2 electrons. So it's going to act the same as these guys that have 8. Does that make sense? Does anyone have any questions on this? So if you just know what column an element is in, you will know how many valence electrons it has.
I have a question.
Yeah.
So the previous diagram that you showed us shows the energy levels.
Right. So what this is saying is whatever element is right here has its like first, second, third energy levels are all full, and its 5p sublevel is not full. And it has 1, 2, 3, 4 electrons in the 5p sublevel. So the rows kind of tell us what energy level we're currently working on filling, and the columns tell us how full that last energy level is. Does that make sense?
Yes, thank you.
Awesome. Okay. So, yeah, so helium has a full valence shell. It's just that because that first energy level only has room for 2 electrons, then it only has 2 valence electrons, but its valence shell is full. So it acts like an element that has a full valence shell because it does have a full valence shell. Okay, so given what I just told you, looking at the periodic table, how many valence electrons does selenium Se have? So I'll give you a second to find it. And then given what row and column it is, how many valence electrons does it have? I'll give you 30 more seconds. Okay, awesome. So 86% of you said 6 valence electrons, and that is correct. So it is in this column right here below oxygen. And if I go back and tell you, put up those columns again, that is the column that has 6 valence electrons. So you can just count over, skipping the transition metals, 1, 2, 3, 4, 5, 6. And so what that means is if you know the configuration of oxygen, then selenium has basically the same configuration, just at a higher level. Does that make sense? Okay. We only have like 5 minutes, so I just want to talk really quickly about Lewis structures. So Lewis structures help us visualize how full our valence shell is. So our valence shell can always have up to 8 electrons. And so this is how we would draw that if we had 1 valence electron, 2, 3, 4. So this shows us 5, 6, 7, 8. Okay. So this is just a way of drawing how many valence electrons we have. And like I mentioned before, full valence shells are really stable. So anytime an energy level is full, that atom is really stable. So these atoms or these elements in the far right column that have full valence shells are really stable. And so they have a full valence shell, which we draw like this. So these we call the noble gases because they're very stable. They're really not involved in like any reactions at all. So just going back to this animation, if I had one valence electron, I would draw it like this. 2, 3, 4, 5, 6, 7, 8. Okay. So I'm going to give you just a few minutes. This is the last thing we have for today. In your groups, you've already determined for these elements how many valence electrons they have. And so I just want you to practice drawing the Lewis structure for these elements. Okay, welcome back. I'll just give people a minute to cycle back in. Sorry, I know that was a little bit rushed. Just giving the last 20 seconds or so to get people back in. Okay. So we already went over the number of valence electrons. So helium has 2 valence electrons, but keep in mind, it only wants 2. It's in that lowest shell. So it's really stable and happy with 2 electrons. So if it makes it clearer, you can draw those 2 electrons together. So it looks more full to you. But the point is that helium has a full valence shell, even though it only has 2 valence electrons. Lithium has 1 valence electron, so we draw it like this. Carbon has 4. So we draw it like this. And then fluorine has 7. So 1, 2, 3, 4, 5, 6, 7. Okay. So that is all we have for today. I'll stick around for any questions. And I know the Lewis structures was a little fast, so I'll go over it again really quick at the start of class tomorrow. But yeah, so problem set 4 is posted. The answers for problem set 3 are also posted. Please stick around if you have any questions.